Hello and welcome back to Exoplanets 101. This is actually the final Exoplanets 101 video, so congratulations, you've made it to the end. Hopefully by the time you complete this series, you'll have a basic understanding of what exoplanets are, what we know about them, how we detect them, and things like that. If you have further questions or suggestions for continuations to this series, I'm happy to make more videos, so please let me know. So today we're going to talk a little bit about the population of exoplanets. So now that we've discovered a large population of exoplanets, over 4,000 have been confirmed to date, we can start to apply some sort of grouping and classification to these planets. Humans love patterns, and we're really good at recognizing them. And we really like to sort things into these neat little boxes, sometimes with detrimental effects, but this is something that's really commonly done in science, and it's called taxonomy. So sometimes classifying things, even without understanding that classification, can lead to insights into these objects that we're discovering. And this is not just true in astronomy, it's true in a lot of fields, but it is very common in astronomy because we're looking out into this great wide universe and we're seeing things and we don't really know what they are. And so we say, well, we saw a few things that are like this and they look like each other. We saw these things and they look like each other and they're different from each other in this way and that. And so from doing this, so then we can actually build upon that classification and start to learn more about why we classify things like that. And so it sort of spurs our understanding as we seek explanations for the mechanisms that cause these different groupings that we just empirically see. It frequently happens that we discover we've been sorting things in a way that made sense to us but isn't actually really physically motivated. For example, stellar classifications were originally classified by the strength of the hydrogen absorption lines in their spectra. However, we later discovered that this doesn't actually correlate with the mass and temperature of the star, and so we kind of reordered it, and that's why we get this kind of strange OBA-FGKM order for the classification of stellar types, because they were originally sorted just based on something that we could classify them by, and then we later had a more physical understanding, and it caused us to kind of rearrange these groupings. So now that we have this large population of exoplanets, what do we see? So these are the confirmed exoplanets from the NASA Exoplanet Archive, which is a great tool that you can use to investigate the populations of planets that we know of. Now, as we've discussed in previous videos, we frequently don't have both mass and radius for exoplanets, and so that's why I'm showing this in two different plots here. So one of these plots shows mass in period and the other shows radius in period. Now ideally we would like to do this all in a very comprehensive 3D space where we had mass and radius and period for all the planets, but unfortunately we just don't have that information yet. So that's why we're looking at kind of two different plots here, but they're showing very similar information. So as you might guess, based on the axes that I've chosen for these plots, the two kind of biggest things that we tend to sort planets by are their size, so either the mass or the radius, or both if we happen to have it, but generally one or the other. And then also their distance from the star. And so this is usually characterized by the period. It could also be characterized by the semi-major axis or the distance from the star, but we usually talk about the period. And so then kind of for the few that we do have enough information to have mass and radius, then we can start getting into density and we can start sorting by composition, and that's really exciting. We've just started kind of to be able to do this for a population of exoplanets, but it's still, still difficult without more of this data. And so generally, we don't try and do too much compositional sorting, although you'll see one example. So one of the major categories that we sort on is the location of the planet, usually, like I said, dictated by the orbital period. And then to classify these, we usually use temperature-related words, right? Because the closer you are to the star, kind of the hotter you're going to be, and the farther away you are, the colder you're going to be. And so basically those are kind of the words you'll hear: hot, warm, and cold. So hot planets are generally located very close to their star, and then cold planets are located out beyond the ice line, so that is the point in the system where water or other volatiles can freeze. And then warm planets are just kind of somewhere in between. So I should mention that none of these classifications I'm talking about are official. These are just kind of accepted nomenclature, things you will see if you start to read about exoplanets, things you'll hear people say, and just kind of a way that we understand planets. But there's no like official definition that anyone has created of these things that's accepted widely, except for common usage. So that's what I'm saying, like, the IAU, for example, has put together an official definition of planet, but hasn't put together an official definition of what's considered a hot planet. In fact, they haven't even put together an official definition of what's considered an exoplanet. So we're talking very informal usage here. Okay, so I said the other thing that we like to sort on is sizes. And so here we generally tend to reference things to the solar system objects and solar system planets that we know, obviously, a lot more about than we generally know about exoplanets. So we tend to use Jupiter for gas giants, and we tend to use Earth to describe other small rocky planets, or terrestrial planets. These are the two most common, but you do sometimes hear for other particular characteristics, things like called Neptune, so that would kind of be ice giants that are in between gas giants and terrestrial. You might hear things called exomercuries, if we're kind of referring to terrestrial planets that are much more dense than the Earth is. So like Mercury in our own system is very enhanced in iron, and so sometimes when we're looking at very dense exoplanets, you might hear things like that. So things like that, but the most common are going to be Jupiter and Earth, and we're just referencing the sizes. Of course, Jupiter and Earth each have a specific size, and so not many exoplanets are going to happen to be exactly commensurate with the Earth and Jupiter, and so we tend to use modifiers to describe this, usually super and sub or mini. So a super Jupiter, sounds pretty cool, super Jupiter, is a gas giant that's much bigger than Jupiter. A super Earth is a terrestrial planet that's bigger than Earth. And so this one is really interesting. So I mentioned before that we're just getting started kind of being able to use compositional differences to classify planets. So it used to be that basically all the planets in between Earth and Neptune size were kind of referred to as either super Earths, so that is big Earths, or mini Neptunes or sub-Neptunes, that is smaller than Neptune. And it wasn't really known where the dividing line was because obviously when we're talking about Earth, we're talking about a terrestrial rocky planet. When we're talking about Neptune, we're talking about an ice giant that has a significant volatile envelope or an atmosphere that the Earth doesn't have. And so it's only in the past couple of years that we've actually been able to kind of probe this region and show that there is a dividing line. And so nowadays it's actually more common to use these specifically, so super Earth specifically to refer to larger than Earth, but we think they're still rocky, and then sub-Neptune or mini-Neptune to refer to smaller than Neptune, but we think they still have a significant envelope. And interestingly enough, super Earths are actually the most common type of exoplanet, even though we don't have any in our own solar system. So it's kind of was a surprise to us that these most abundant exoplanets are something that we don't even see in our own system, although potentially Planet 9 might be a super Earth. But okay, so frequently we like to combine these two axes, so that is the location and the size, and describe various subpopulations. So for example, there are hot Jupiters, and you can see that on these plots here, this kind of cluster of objects that are very close to their star, that is they have a very short period, and they're very large, that is they're Jupiter-like, they're giant. Hot Jupiters were actually the first type of exoplanet discovered around a main sequence star back in 1992, and they were a surprise, really. It's still kind of an ongoing question of exactly how hot Jupiters get there. We don't really think that they can form in situ there because it's just too close to the star. So probably there needs to be some sort of mechanism to get them into that location. Also, hot Jupiters don't tend to be stable on extremely long time periods, and so they're probably eventually going to be devoured by their star. If you look at these plots, you can see that there are a lot of hot Jupiters, and so you might think hot Jupiters are very common. But in fact, hot Jupiters are just very easy to detect because they're both very massive, very large, and they are very close to their star. And so if you think back to the detection methods we talked about, that kind of increases the ease of detecting them. And so this is actually an observational bias, and we think that hot Jupiters are actually intrinsically quite rare. So if you have hot Jupiters, you can also have cold Jupiters, and our own Jupiter would be considered a cold Jupiter. Now, cold Jupiters are a lot more difficult to detect because they're located in the outer reaches of their stellar systems. One, that means that the amplitude of the signal is going to be decreased if you're talking about radial velocities, and the probability of transit is going to be decreased if you're talking about transits. It's also that you need a long baseline, so things that are farther on their system have a longer period, and we usually use this periodic motion to detect planets, and so you need to observe for a long time to observe things that have a longer period. And so this is why we haven't discovered a lot of cold Jupiters, just due mostly to detectional issues. In between, we have, you can see here in these plots, we have things that aren't quite hot Jupiters, but they're not cold Jupiters either, and we call these, as you might guess, warm Jupiters. So one thing that's really interesting about warm Jupiters is they tend to have higher eccentricities, and we're not exactly sure what they are. Are they cold Jupiters? They're in the process of becoming hot Jupiters. There's been some mechanisms that have been proposed that might explain this, but do they actually do a good job of recreating the warm Jupiters that we see? So this is actually, warm Jupiters are really interesting and very actively being studied. There's a really interesting category of exoplanets called ultra short period planets. You can see a few of them here on these plots. They basically just have very short periods. So a USP is usually considered to be anything with a period less than a day. We don't usually apply a size categorization to these, but that close to the star, they're going to basically have a very difficult time holding on to volatiles. They're just going to be evaporated. They also are so close to the star that they're going to be pretty easily torn apart, so they have to have maybe a certain minimum density in order to not be torn apart. These planets can also be deformed because they're so close to their stars, so they might not be spherical anymore. And so USPs are really interesting. I think they're pretty cool. We definitely don't have anything like a USP in the solar system. Our closest planet to the sun is Mercury, which has an orbit of 88 days. So remember, USP, we're saying less than a day. So when we talk about exo-Earths, that's another subclass of planets, and we're usually talking very specifically about Earth analogs. So not just similar to Earth in size, but also similar to Earth in the fact that they're located in their star's habitable zone. So for a star like the sun, that would be similar to the Earth's location, but for a star like an M dwarf, which is a very small and dim star, the habitable zone is actually located a lot closer in, so they would be on a lot shorter period than the Earth would be. These planets have actually been so far very difficult to detect, especially for sun-like stars. 1 year period is pretty long to detect. There happens to be certain systematics associated with detecting planets that have a similar period to our own. And basically finding exo-Earths is really one of the main missions of exoplanet science, because if we discover more exo-Earths, we can kind of determine this value that we call eta Earth, which is basically the occurrence rate of potentially habitable rocky planets, which is not very well known at this current point in time. I mentioned M dwarfs. So M dwarfs are actually the most common type of star, and their habitable zones are much closer in, and so it's easier to detect Earths that are in the habitable zone of M dwarfs. And so a lot of habitability and exo-Earth type studies are focused on these M dwarf stars just because it's easier to detect. There's more of them, things like this. So a lot of effort is going into targeting those systems. We're really hoping that future NASA missions might help us kind of really narrow in on these exo-Earths. 2 projects that have been proposed are called LUVOIR and HABEX. Both of those were put forth in the 2020 Decadal for the astronomical community. And we're hoping that eventually we can get to the point where we can not only detect these via, say, rate of velocities or transit, but also via direct imaging, which is currently beyond our capabilities, but would be really exciting if we could do that, because it would help us discover more about these planets and things like biosignatures and habitability, which of course we're all very interested in. And then one last subclassification that I want to talk about, just because I think they're super cool, are these things called super puffs, which, that's just a fun name. And I think actually my PI might have been the one who proposed the name super puffs. So. But anyway, as the name suggests, these are very puffy planets. That is, they have very large radii and very low masses. So we, like I said, we don't have a lot of planets that we can do density work on, although it's increasing more all the time. But these ones are kind of oddities. They're pretty low mass, but they have these big radii. We don't exactly know where they come from or what they're made out of. It's been proposed that they might be ringed planets, so that would make the radius appear a lot larger, even for a smaller mass. But it's really not known, but I think they're cool and they're fun and they're super puffs. I just like to imagine like clouds of cotton candy being a planet. Cotton candy planet. Yum. Okay, well hopefully you can see now how kind of breaking the exoplanet population down into subpopulations helps us to kind of understand a little bit more about the exoplanets around us and in the universe, and that we're continually seeking to improve our understanding and get more data and understand better. So this has been the Exoplanets 101 series. I hope that you are more acquainted now with exoplanets, and I hope that you will check out some of the other series on my channel. All right, I'll see you again soon. Bye.